Hello once again, Blake and Daniel. Let's go ahead and let's take a look at our second day here with Green's theorem. So here we have 17.1. I did adjust the schedule. We are going to only spend 2 days in 17.1. You'll notice that when you look on Google Classroom, and tomorrow we'll go to 17.2. But today's our second day with Green's theorem, so let's go ahead and let's take a look. So we're going to look at how we handle non-closed curves. One way to handle them is simply, parameterize the curve and go ahead and do the individual line integrals. But there is a way to use Green's theorem in the case that it's a very simple line that is required to close the curve. So let me illustrate what I mean by that. So in that case, we can close the curve and we can solve. So here's the situation that's given to us in problem number 12. So in problem number 12, we have a vector field, and we want to find the line integral over the vector field f dot ds here for this line, basically this oriented curve starting at A and following this path to B. Well, obviously that path has 1, 2, 3, 4, 5 separate segments. So to calculate that, I would need to do 5 separate parameterizations for each segment of the line, and so I'd have to, in essence, do 5 separate integrals. And the idea here is maybe I can save some time with Green's theorem because it's only this one little vertical line segment that's missing in order to have a closed curve, and then Green's theorem would apply. So let's see if I can go ahead and see how to do this using Green's theorem to save myself from having to do 5 separate integrals. So notice if I were to close that curve, and I had the closed curve there from A to A essentially, following that path, that would be equal to the curve as listed there, curve C going from A to B following that path, the integral of that, plus the integral of the curve just going from B to A of the same vector field. But notice the closed curve here, the integral of the closed curve, that's equal to this expression here by Green's theorem. And so if it's equal to that by Green's theorem, I can go ahead and I can say that if I solve here, this here would be equal to these two expressions here. So given this situation, I can solve for this and say that that this would be equal to this expression in Green's theorem minus this section here, which if I do that, that's going to equal my closed curve. So that's just solving this for my closed curve. So I can see that if I can evaluate this, which is a simple application of Green's theorem and a simple parameterization of a vertical segment, I can get it. So let's go ahead and let's do that. First, let's go ahead and let's find this double integral here using Green's theorem. So what I'm going to do here is I'm going to recognize that this is going to be the domain here of 4 times dA. Now that's just, this here becomes 0. Sorry, this here becomes 4, the derivative of x with the 4x there with respect to x. This becomes 0, so it's just 4. Now, the nice thing about this is only a constant off of being the double integral of 1 dA, which is the formula for area. So I'm just going to factor that 4 out and get to this, which this is an expression for area. So I can express the area of that region. I can see that it's going to be basically a 3 by 1 rectangle and a 1 by 1 square there. So it's going to have an area of 4. So it's going to be 4 times 4, or 16. Now I need to find the value for this integral. So for that integral, I must first parameterize the curve going from B to A. So that's going to be this curve of the form C of t, which is going to be x remains a constant, -1. Y is t, where t goes from -1 to 0. And that parameterizes that. So then to calculate this here, I know that the integral going from b to a over this vector field is going to be equal to going from negative 1 to 0. First thing I'm going to do is I'm going to take the x term here with this plugged in, so I will take negative 1 times the derivative of negative 1, which is 0, plus, and in this case here, it's going to be 4 with negative 1 stuck in, so that's going to be negative 4. So it's going to be plus negative 4 times the derivative of the y term, which is just 1. So negative 4 times 1 is negative 4, so it's going to be minus that 4 times 1. And so this evaluates pretty easily to be the integral there. And it's going to be of negative 4, which means it's going to be negative 4t evaluated from negative 1 to 0, which if we go ahead and do that, we end up with 0 minus 4, or negative 4. So now I can finish it off. Notice, remember, I said that my curve that I was interested in was this minus this. So I have 16 minus negative 4, and that's going to be 20. So that's how we handle a non-closed curve when there's a simple curve that closes it. Okay, now let's look at another situation. Let's look at area. So when looking at area, we're given this equation, which is a special application of Green's theorem. So it's the area that's contained within a closed curve C is going to be 1/2 times the integral over that closed curve C of x dy minus y dx. So let's go ahead and let's apply this. So on number 16, if you take a look in your book at number 16, you can see it says, basically we have a triangle with the vertices 0, 0, 1, 0, and 1, 1. You remember we did this same triangle in the last homework, so I'm not going to re-sketch it for you and do all that again. I think we remember pretty much how it sets up. But I know this is going to be 1/2 times the double integral. Notice this becomes a Green's theorem situation. But notice here, you have to be careful. The x term is this negative y here. That's actually the x value in our slope field. So when I take the derivative of that with respect to x, with the derivative, I need my dy, my derivative of y with respect to x. So this is, my y term is x with respect to x is just 1. Then I have minus, and the derivative, this is my x term. When I take the derivative of that with respect to y, I get negative 1. So I have 1 minus negative 1, or it just becomes 2. So notice this becomes the double integral. And I quickly applied this here, where this is 0 to 1. If you remember, that handles that triangle that we talked about before, 0 to x of 2 dy dx. And interestingly enough, here, what I probably should have done, well, we're showing this as the area. Obviously, what I could do is I could simply factor out the 2, and then I would know this is the area, but I've already said it's the area. That's what I'm calculating. So I would like to carry out Green's theorem to its conclusion to show that it really does give the area, not say I'm getting the area by getting the area. But we'll see that in theory this would produce the area if I factored out that, because then I would just have the double integral of 1 over, over the region D, dA. But evaluating the integral here, notice I have 1/2 times. Integrating this with respect to y, I get 2y evaluated from 0 to x dx. Substituting in, I get 1/2 going to 0 to 1 of 2x dx. Anti-differentiating there, 1/2 times x squared going from 0 to 1. Plug in the 1 and I get 1/2. And knowing that triangle with vertices of 0, 0, 1, 0, and 1, 1, that does have, it's got a base of 1, a height of 1, and so we do know it has an area of 1/2, so we verified it there. All right, that's how we find area using Green's theorem. Now let's look at a different type of area situation, and this one is found if we look at example of 24. And so in order to understand this one like this, what we're going to see here is look in your book at the let's start off here. Look at figure 12 to start with. So when we have these missing areas inside of a region, so it's important to see that, as you would kind of guess, the orientation of the curve matters. So if you take a look here, and what we see is that if the curves are oriented in the same direction, then it's like what we would think. It's the big region minus the little region. If the curves are oriented in the opposite direction, then we actually end up adding the inside region instead of subtracting it. So for instance, if you looked at on figure 12, the first one there, if we're talking about there, notice that the C1 is in the counterclockwise direction, the C2 is in the clockwise. They are in opposite directions. So if we want to talk about D1, it will actually be C1 plus C2. Whereas if we look at the example B there, we have the C3, and then C5 is in the same direction. So we will subtract the C5, and the C4 is in the opposite direction, so we will add the C4, if you want to think of it that way. So it's important to understand that orientation and how that works there on that type of figure. So let's go ahead and let's take a look at number 24 in your book. So number 24, we have a rectangle, and inside of it we have a circle. So the rectangle is a 6 by 10 rectangle, and the circle is a circle with radius 2. And notice they're both oriented in the same direction. So if we want to talk about that region D, if we want to look at that region D there, it will end up being C1 minus C2 because they're oriented in the same direction, so I'll subtract the missing circle if you want to think of it that way. So that means that our line integral there was C1 minus our line integral there of C2 is going to be equal to our D, basically our oriented region D, which we'll apply Green's theorem to that and express that as the double integral over D of using Green's theorem df2 dx minus df1 dx dA. So now what we're trying to find here on 24 is we want to find this right here. We want to find this C1, but we are told what this interior part is, and we're told what this is here. So we're given that this expression here is 12. So substituting in, I know it's going to be this curve here if I add that to that side plus that curve there. So that's going to be equal to, and we're told that this is -3 and this is 12, so I've substituted in there. Now once again, take advantage of area. Factor out the -3. And so then I know I've got the area here of the region D. Now the region D is a rectangle with a missing circle. So the rectangle there is a 6 by 10 rectangle, so that's 60, minus the missing circle, which is a radius 2 circle, so it's 4 pi. So I've got -3 times, this is my area of the region D, plus 12. And calculating that out, we get 12 pi minus 168. Okay, finally, last type of question. Know this definition of curl. Just this inner part of Green's theorem we talk about of curl, and consider figure 10 to understand, and let's talk about curl. The best way that I can think of curl is it's a measurement of what happens if you were to put something in like the water. So if you want to think of it, if you put a small little paddle wheel centered on the origin right in the plane, if you look at figure 10, the curl is positive if the curl would go and cause it to turn in the counterclockwise direction. The curl is negative if it would cause it to turn in the clockwise direction. And the curl is 0 if it wouldn't turn at all. So if we imagine putting a little paddle wheel in there, you see in the figure A there of figure 10, the vectors wrap around the origin in the counterclockwise direction, that vector field, and it would turn it counterclockwise. So we have a positive curl. For B, it's a kind of a vortex, but once again, it is twisting around in the counterclockwise direction. So what we'd find is the smaller the paddle wheel, the smaller the curl would be, but regardless, it would be a positive curl. And then for C, notice we've got that vector field where the positive vectors are pointing positive, and where, based on y value, the ones below the x-axis are pointing negative. And if we put a paddle wheel in there, we can see that it would spin the wheel in the clockwise direction, so we have a negative curl. D, we would see that it would not spin the wheel at all. The forces would just be pushing in or pulling out equally on it, and so it would just be 0. Same thing for E. We'd have curl of 0. So just understand how that relates to curl. Here's your homework: 13 through 17 odd, then 25 and 27. Okay, hope that goes well, and go ahead and send me a message on Classroom if you've got a question about something. Thanks.